Okay, so good evening, everyone. Welcome to this live problem solving session for the course Essentials of Topology. So, this is instructed by Professor S.P. Tiwari from IIT ISM Dhanbad, and I am TA for this course. I am a research scholar from the Department of Mathematics, IIT Kharagpur. So, I will solve some problems, but before that, if you have any doubt, just you can ask now. So one of you are saying you have doubt in lecture 29. So can you say what is the doubt?
Sir, x tau is a topological space, then a function f from x tau to x tau dash such that f of x equal to x, that is identity function, is continuous
Yes.
not only if tau is finer than tau dash.
Yes.
But what is the proof sir has written? That is, I think there is some in the class, by listening the class, sir has done reverse, I thought.
Uh, I cannot recall what he has done, but the statement is true. So do you have doubt in the proof? That I can check.
Yes, sir. Means sir has done tau dash is subset of tau we have to prove, but sir has done tau is subset of tau dash. That much.
Uh, okay, so someone is saying that he has uploaded a different video with
I think that is some mistake has been. That is what I'm asking.
it may happen. It may happen, but did you got the correct way?
Yes, sir.
Yeah, okay.
Means
Then
while doing that proof, sir has done differently. For
yes,
that,
okay.
sir, where do I get the correct proof? What he is saying? One more person is saying.
Okay, then it is fine. If you understand the correct one, then it is fine. But there may be some error in the lectures. Maybe you can ask those issues in the question discussion forum, because then only the instructor will be able to see those issues. Okay.
Oh, okay, sir.
Yeah. I think one of you has already raised that issue, and I think it is resolved now. Maybe if it is not resolved, maybe you can send one more reminder or something like that. And yeah, it's good. If you find some errors, please just post it in that discussion. Yeah, yeah. So there is a second video for lecture 29 which has correct code. Maybe you can look that one. Okay, any other things or any other queries? Okay, so then let's quickly summarize the topics, then I will go to the problems directly. Meanwhile, if you feel any doubt, just raise your voice. So in this week we started with the countability axioms, where like those topological spaces where countable sets play a key role. So here we have studied about three types of topological spaces. One is first countable space, then second countable space, and the third one is a separable space. I hope you can recall the definitions. These are not at all difficult, and we have seen lots of examples of these things. Also, some properties and relation between these spaces. Okay, what we have done? and we have also defined convergent sequences. So in the lectures we have not done much about convergent sequences, so I will do in this live session. And then we moved on about continuous functions. So we have seen the definition of continuity at a point. Then we have seen the definition of continuous functions. And we have seen various characterizations of continuous functions. Characterization of continuous functions. And also we have seen various ways of constructing continuous functions. And you will see some more ways in the next week. And all of these things are very important. Continuous functions. So overall, these are the contents of this week. So if you have any doubt or query, just feel free to ask. So I will start with problems on sequences. Let's see how sequences behaves in different type of topological spaces. Okay, so let's start. Okay, so the first one is consider the set uh, of natural numbers with the uh, final segment topology. So with the final segment topology, so that means this topology is basically generated by, okay, maybe I can put it as tau, i.e. tau is generated by this basis. So we have done this example in the second week. If you not able to recall this, you may later go back to the second week lectures and see the proof that how it is a topology, how it forms a topology. Now show that the sequence, let's say 2, 4, 6 and so on, this sequence converges to every point. This sequence converges to every point in N. Okay, so basically we know the topology and we know the basic open sets, and we have a sequence. We have to prove that it is everywhere convergent. So the sequence is basically xn equals to 2n, and it will converge at every point. Okay, so what should be our approach? So we have to use the definition of convergent sequence. So since it converges at every point, let's take an arbitrary point. Let small k belongs to n. Then we will show that this sequence xn converges to this k. But this k is arbitrary, so it is everywhere convergent. But how to show that this xn is converges to k? Yes. So what we have to show? So if so, what is the definition? When we say xn converges to k, so the definition is if you take an arbitrary open set G such that k belongs to G, then there must exist a natural number such that all the elements of the sequence or all the members of the sequence must belong to this G for all n bigger equals to n. So that means for every open neighborhood of this element k, you should find an index such that the members of the sequence all lies in that open neighborhood after this index n naught. So can you find some index in this case for this sequence? So let okay, so let G belongs to tau such that this K belongs to G, right? Now, if you use this basis, so then there should some basis element which contained in that G. So there exists some n naught belongs to n such that n naught plus 1 and so on. This basis element is subset of G and your element K should belong to this basis element, right? Now, can you say what will be that index? But if you take 1,
K.
uh,
K.
no, not exactly K. What about if you take n naught itself?
But what is the guarantee that K will be in that?
So what do you need? You need xn belongs to this G for all n bigger equals to that index n. So we need to find this index n. So if you take n naught itself, then you can see that. So now 2n belongs to this n naught plus 1 and so on, right? For all n bigger equals to n naught. And this is your xn. So maybe I will write this sequence as so did you get the point? So 2n naught belongs to this set. 2n naught plus 2 also belongs to this set. And this is subset of G. So this implies xn converges to k. But k is arbitrary. since k belongs to n is arbitrary, xn is everywhere convoluted. Okay, so did you get the point?
Sir, what is exactly
What is exactly?
and not?
So k is k lies in this open set G, and
Yes, sir.
this beta is a basis for your topology.
Hmm.
So from the definition of basis, you will find a basic open set such that this condition holds, right?
Hmm.
And you are getting this n naught from that basic open set.
What can be the exact and not?
N naught depends on this value of k. Suppose you take k equals to 5, then what
Hmm.
will be a basic open set containing this 5? That obvious option is 5, 5 plus 1 and so on. And you can take a smaller one also. You can take 4, 4 plus 1 and so on. So any index which is smaller than equals to 5 will work.
It will depend upon G also, na?
Yes, but if you take a natural number k, then k comma k plus 1 dot dot so on, this is the smallest basic open set which contains k. Every other basic open set will contain this basic open set.
That is what I am saying, that if you take and not as K, then it will be more precise.
Yeah, you can say this, but for the proof, I think this much is fine. Even if you can take one also, but that's okay. So, is there any other doubts? Okay. So, one thing you can observe that this sequence has infinite range, right? So maybe I will put this as a remark, and you can verify this. Uh,
Sir, Harsh has written something. Can you check it? What he has?
okay. Why would not n not equals to 1 not 1? If we take 1, then the basis element would be physical master element. Okay. No, but xn may not belongs to x1 may not belongs to that G, right? So let's take a particular example. So your it would not be containing every G. Yeah. So did you got the point, or shall I give some more justification? Okay. Okay, then so just try with some particular cases. You take some particular value of a and try to prove, see what is happening. Then it will be more clear. Yeah. So what I am saying is, in n with final segment topology, means with this topology in the last exercise, if xn is a sequence with finite range, okay, then the sequence cannot be convergent. then xn is not convergent. Okay, so one easy justification is that you see every open set. Uh, okay, what I'm saying is correct, or maybe let's take an example. So suppose your sequence is uh, let's say 2 4 2 4 and so on. So odd indices are 2 and even indices are 4. Then is this sequence convergent in the final segment topology? So let's check with let's see if this sequence action converges to 5 or not. So we can take this open set 5 5 plus 1 and so on. This contains 5, but this does not contain the members of xn at all. So xn cannot converge to 5. But what about points which are less equals to 4? So I think xn will converge to 2. Okay, so this statement it seems it's not correct. Maybe it is. So let's take I will just put this as an exercise. So check the sequence xn which is 2 4 2 4 and so on is convergent or not. So it seems it will converge to 1 as well as 2. Okay. So we just try to prove this. So this is for the final segment topology. Now what happens with the initial segment topology?
So converges to 4 as well.
Sorry.
Every number which are less than 5, this sequence is convergent. Or
No, this sequence will not converge at 4.
why?
So you take the open set 4, 4 plus 1 and so on. This contains 4, right?
Yes,
But
sir.
elements of the sequence, these are not belongs to this set because 2 does not belongs to this. And you have 2 at every odd indices. Did you get my point?
Sir, but the definition is that for every open set containing that limit, whatever the limit is, there
Yes.
is a basic element
Yes,
which is
such that
contained.
xn belongs to this set G for all n bigger or equals to some n naught, right?
Mm,
This should happen.
mm.
But you will find 2 in these cases because 2 is everywhere at every odd indices.
And not is 4 you are taking in this case.
Sorry,
Whatever not is, this will not
this will not.
happen. I mean, this will not satisfy.
So yeah, so you cannot find some index k or sorry index n naught such that xn belongs to G for all n equals to n naught
Yes, sir, yes. Got it.
because x2 n naught plus 1 is equals to 2 and this does not belongs to that set.
So 2 is also not a limit point.
2 is a limit point. because whatever open set contains 2, it should contain 4 also. Okay. Okay, now consider n with the initial segment topology, topology tau. That means it is uh, generated by the basis 1, 2 up to n, and you are varying this n.
Sir,
Yeah, any questions?
2 is also not a limit point of this sequence.
2 is also not a limit point.
Yes, sir.
Why?
Equation should belongs to that open set, na? Sir.
Which one?
Or all n greater than or equal to n naught.
Yes. So what is the smallest open set which contains 2?
2, 3, 4, 5, and so on.
So 2, 3, 4, and so on. So xn belongs to this for all n bigger equal to 1.
If you take n is equal to 5, then
N equals to 5, then it is, means x5 is 2, right?
uh,
So your xn is what? It is 2n. Sorry, not 2n. It is 2 for n odd, and it is 4 for n even. This is your sequence.
sir, the definition of the convergence of the sequence is not clear. Can you please elaborate?
I did not get your point. Sorry, can you repeat?
Sir, not clear.
Not?
Convergence definition of the convergence of the sequence is not clear. Can you please explain?
Yeah, okay. So maybe I will write here. So what is convergent sequence? So you take a topological space x comma tau, and you take a sequence xn in x. Okay. Now, uh, when we say this sequence xn converges to some point, let's say x, if whatever open set you take, if for every g belongs to tau such that x is also in that g, means whatever open neighborhood of x you take, there exists a n naught belongs to n, but this will depend on g, such that your sequence xn is also in g for all n bigger equals to n. So after a certain stage, all your members of the sequence should belong to that set g. Okay, so this is the definition.
Okay, sir.
Yeah. So now, is it clear why this sequence converges at 2?
Sir, you said that the smallest open set containing 2 is 2, 3, 4, and so on.
Yes.
So, if we take n0 is equal to 2, then this will work.
So
Then
I
not.
so you just verify this definition. You just don't bother with the topology one. You just verify this definition. You take a particular open set which contains 2, then you need to find a n naught, right? Now, if you take a particular open set G which contains 2, then this G should contain some basis element,
mm,
and that basis element looks like n naught plus 1 and so on, but this basis element also contains 2.
mm,
So some n0 plus I has to be 2. So what about this n0? This is just 2 minus I. So, so what I mean is, if n0 plus I is 2, then n0 plus 3I is 4. So all the members of the sequence lies in this open set.
yes, sir.
So all the members lie, but for every n greater than n naught means whenever we are going to take
Yeah,
great.
these elements are in that open set means this xn belongs to this G, right? And this is true for all n bigger to 1, because 2 is also in G and 4 is also in G.
Okay, sir. But if I take n naught, that is for suppose 5, where 2 and 4 doesn't belong to that sequence, I can form a sequence
2 and 4 does not belongs to
2 and 4. For suppose if I start from 5,
means you are
very n
taking
greater than
some
or
other
equal to 1.
example or what?
Sir, in that example only, means
Yes.
I have to take only 2 and 4, the open sets which are belong to the open set 2 and 4. It
Yes.
must, for that only, for that case only.
Yes.
Okay, okay, sir. Otherwise, if I take any open set 5 means, then it will not hold.
No, you are checking that this sequence converges to 2 or not. Then you should bother about those open sets which contains 2, right?
Yes, sir.
And if your open set contains 2, then in this case your open set also contains 4.
Yes, sir.
So all the members of the sequence has to be in that open set G. And in this case your result is true for all n bigger equals to 1.
Sir, all the open sets in this topology are like k plus 1, k plus 2, and so on.
Yeah, it is actually decreasing form. So first one is 1, 2 and so on. Then it strictly contains 2, 3 and so on. Then it strictly contains 3, 4 and means
So,
the
sir,
infinite set. So it is a
the
descending chain actually.
collection of the open sets is actually basis,
Yeah, this forms a basis for this topology.
and this is precisely all the open sets. This V contains all the open
Yes,
sets.
yeah, in this case these are the not all, and empty set is also there.
Empty sets within. Okay.
Yeah, so these things I think it is mentioned in that lecture also. Maybe you can go back and take a look. So yeah, so let's focus here now what I wanted to do. So now let's focus with the initial segment topology. Then we know the basis of this, and here the exactly opposite thing is happening. The basis elements are in the uh, increasing order. Okay, so if xn is a sequence with infinite range, then it cannot be convergent. Then it cannot be convergent. Okay, so this one is very easy. Can you see why it is true? Because the open sets are finite. Yes, exactly. The open sets are finite, and your sequence has infinite range. So it cannot so the open set cannot contain infinitely many elements. So maybe let me quickly write the solution.
Sir,
Sorry.
of all natural numbers is also an open set. How can
Yeah,
you say
but
that?
you need to focus on every open neighborhood, right? So I say that whatever for every open neighborhood you take, you should be able to find a index. Okay, so we will proceed by contradiction. Suppose xn converges to some k. Okay, so now you take G as the open set 1, 2 up to k. But your sequence has infinite range. Since the sequence xn has infinite range, then there exists some so what I mean is, so there is no n naught belongs to n such that xn belongs to G for all n bigger equals to n naught. Because so sequence means what? Sequence is a function from n to your set x, where 1 goes to x1, 2 goes to x2. And if you take this range set xn such that n belongs to n, this is an infinite set. So it will contain elements which are bigger than k. So whatever index you take, you will find an element which is bigger than k, and it is lies in that sequence. Maybe I can write it more precisely. But did you get the point? Should I write more explanation?
So, sir, first we need to prove that every open set except n is finite. Then we can claim this.
Yeah, every open set is finite here. You see the open sets are here. These are the open sets including your file.
This is a basis element. Every open set will be union
Yes,
of
yes, but
arbitrary.
the thing is here the open sets are in the increasing form. So 1, 2 up to n. So how these open sets looks like? First one is 1, second one is 1 comma 2, third one is 1, 2, 3, and so on. So if you take union, it will be the largest one. If you take intersection, it will be the smallest one. And all these are basis elements. Yeah, is it okay? Or should I write more for this one? Yeah. Okay, maybe because I wanted to do some other problems also, because these are very easy. You just have to convince yourself. Okay, so let's move on. Yeah, now let's see the cofinite topology. Okay, so let X be a set with the cofinite topology. Cofinite topology, so I will denote it by tau CF on X. So you will find similar type of problems in the assignment. So it will be useful for you. Okay. Now prove that a sequence xn in X converges to a point x belongs to x if and only if for each y not equals to x, the set n such that xn equals to y is finite. Okay, so let's try to understand this. So what we want to do is we are taking a set with the cofinite topology and we want to characterize all the convergent sequences. Okay, so we want to characterize all the convergent sequences. So let's take an arbitrary sequence xn and we want to check when the sequence will converge to some point x. And this statement is saying that this your sequence xn converges to x if and only if you take any other point. So whatever point you take other than x, this set such that xn equals to y, this should be a finite set. If this set is finite for every y, means this set is finite for every y other than x, then your sequence will converge at x. Okay, so the proof is actually straightforward, very straightforward. So did you understand the statement?
Yes, sir.
Okay, so one side is yeah,
Actually, the eventually constant sequence is convergent. You want to say that?
no, that is not the thing. So you can take let's take x equals to r with cofinite topology and you take xn equals to n. This is not at all constant sequence. In fact, every member of the sequence is distinct and you will see that this sequence converges to everywhere. Okay, so let's try to prove this. So first I will prove this direction. So I am assuming xn converges to x. Yeah, do you want to say something?
You have written y not equal to x, the set n such that x1 is equal to y is finite.
Yes,
Means those terms which are not equal to x are finite.
not equals to x. Now this y is particular. This y is fixed and this is true for every y.
Okay.
Okay, so let's try to prove this. So suppose your sequence xn converges to x and you take an arbitrary element and let y belongs to x such that y is not equals to x. So what we have to show is we want to show the set n such that xn is equals to y is finite. Okay, now how to show this? We need to use the convergence of the sequence. So what we will do is we will take the open set G as x minus y. So basically the complement of y. So this is a open set. Then this is belongs to tau and your x belongs to G, right? Because y is not equal to x. So for this open set, So then by the convergent definition of a convergent sequence, so there should exist some index such that your xn belongs to G for all n bigger equals to n naught, right? So what does it mean? So xn belongs to x minus y for all n bigger equals to n naught. So this means xn belongs to complement of y. So this means xn not equals to y for all n bigger equals to n naught. So xn equals to y, this set has to be finite, because after n naught all the elements of xn cannot be equals to y. So this implies if you take this set xn equals to y, this cardinality has to be less equals to n naught minus 1. So only the first n naught minus 1 elements of the sequence can be equals to 1. So this is fine. Is it okay?
Sir, why you have taken G?
Sorry.
So to show convergence, we should take an arbitrary open set which
No, I am
contains.
assuming the sequence converges to X. So I am
Yes, sir.
proving this direction, right?
Okay, okay, sir. Okay, sir.
Now we will prove the reverse direction. So now conversely assume, so conversely let for every y which is not equals to x, this set n such that xn equals to y is finite. Then what we have to show is, then we want to show that xn converges to x. Now you take arbitrary open set which contains x. So let G belongs to tau such that x belongs to G. So what we have to do is, we have to find an index. But G is an open set. So what is the structure of G? What can you say? Because we are in the cofinite topology.
Complement is finite.
Yes. So G is basically some x minus x1 up to xn. This x1 up to xn can be empty set also, uh, where this xi is not equals to x for 1 less equals to y less equals to n, because x has to be in this set G. So G has to look like complement of some finite set. So now if we use this condition, then what can you say? So now by the given condition, so let's use whatever is given. By the given condition, the sets uh, n such that xn equals to x1, this is finite. Not only this set, actually all the sets, also n such that xn equals to x2 and up to so on, n equal such that xn equals to, okay, here is a problem, I should use some other notation. So let's take k. Okay, so xn equals to xk. So these are finite sets. So up to this, is it clear? Okay, so this implies there exist some m1 dot dot up to mk belongs to n such that xn is not equals to x1 for all n bigger equals to m1, xn is not equals to x2 for all n bigger equals to m2, and so on. Xn is not equals to xk for all n bigger equals to mk. So this we are getting from this condition. Now you take the maximum of this thing. So take m equals to maximum of m1 up to mk. Then what you can say is, then xn is not equals to x1 for all n bigger equals to m, and this is true for xk also. So this implies xn should belongs to x minus complement of this for all n bigger equals to n, and this is your open set G. So this is what we wanted to prove. So we have taken an open set G which contains x, and we wanted to find an index m such that all the elements of the sequence contained in G for all n bigger equals to n. So is it clear? Okay. So we have characterized all the convergent sequences in cofinite topology. Maybe let's see one particular example so that it will be more clear. So let's take R with the cofinite topology, and let's take your sequence xn as 1 by n. Then can you say is it convergent or not? Yes.
Yes, sir.
And where it is convergent? Where it is converges?
Converges to zero.
Only 0. It converges everywhere. Then xn converges everywhere. How we will check this? So suppose you want to prove that uh, you take an element, let's say 0. You want to prove that xn converges to 0. So how to use the previous condition? So if you take any other real number which is not equals to 0, this set n such that xn equals to y, this should be a finite set. Is it finite set?
It is always in empty set, sir.
Sorry.
Empty set, sir.
This set is empty
Yes, sir.
for any y which is not equals to 0.
Yes, sir.
What about if you take y equals to 1?
One is not equal to zero, no, sir.
Yes, but I'm saying about this set xn equals to y.
Sir, xn, sir, for all n, xn is not equal to zero, sir.
Yes, that is true. So,
That is empty, na. There is no n for
but I'm
which
not
x.
talking about that set. I'm talking about this set n such that xn equals to y, where y is not equals to 0.
So it is always infinite.
It is always infinite for fixed y.
Yes, sir. No, sir. No, no, sir. For
So if
fixed y, right.
so if you take y equals to 1, then what about this set n such that xn equals to 1? This is, in this case, it is just a singleton set, right?
Yes, sir.
But if you take y equals to, let's say, 2,
Then
then
it will.
this set xn equals to 2, it is an empty set.
Yes, sir.
So whatever you take, this set will be finite. And the reason is, if every element of a sequence is distinct. So this sequence will converge everywhere. So you just try to use this previous result. For each y which is not x, this set has to be finite. Okay, let's see one more example so that it will be clear. So take xn equals to 0 for n odd, and it is n for n even. Now what about this sequence? Is it convergent?
Sir, except zero.
Sorry,
So it is convergent. Except zero.
sorry, your voice is not clear. Can you repeat?
Sir, this sequence is converges to every point except zero.
Yeah, exactly, exactly. You are correct. Yeah. So then xn converges everywhere except 0. So you just use the previous result. That's all. So this is all about the cofinite topology. So is there any doubts so far?
Sir, the last example, can you explain again?
Yeah, this one.
Yes, sir.
Yeah. So what is your doubt?
Why it is except zero? In the
So
finite topology, the elements look like x minus finite set.
sorry, it should converge to 0, but not at other points. No, you correct or what? Okay, so what we have to check? So we have to take y which is not equals to 0. So it is convergent at 0, right? Because n such that xn equals to y, this is a finite set. Yeah, so it will be convergent at 0. Yeah, this is also everywhere convergent. So yeah, I was thinking something else. Sorry. Yeah, it is also everywhere convergent sequence. Yes. Now is it clear?
Something confusion I'm getting, sir.
Sorry?
In the example, I'm getting confusion. Why? Because the theorem says whenever we are going to take two different, that is y not equal to x, that
Yes.
shape should be finite,
Yes. Yes.
and the sequence should be convergent, which is in the other case. Means that element should be like that, infinite set minus finite set. Means in cofinite topology, the elements open sets should be always only in x minus something or whole x.
Yes. Exactly.
Sir, how we are interlinking these two? Means when it is zero and when it is even.
So you want to prove it is convergent to 0. Okay. First, let's see that thing. So first one is xn converges to 0. So for that, what we have to check? So we have to check for arbitrary y not equal to 0. This set is finite or not. Okay. So it is convergent at 0, right? Because if you take y which is not is 0, not equals to 0, and xn equals to y, this is finite because every element of xn is either 0 or n. So it all even indices are distinct and odd indices are exactly 0. So if y occurs in this sequence, then it can occur at most 1.
Sir, I think it is only convergent at 0.
Only
Not
convergent at 0.
yes, sir.
So it is this cardinality is at most 2. Now you take x which is not equals to 0, and suppose your sequence xn converges to x, suppose for contradiction, then what you can do is you just take y equals to 0, then this set xn equals to y, so means xn equals to 0, this set is infinite, so it is violating the theorem. So this contradicts the theorem. So xn cannot converges to x where x is not equals to 0. Okay, now is it clear? So the statement is actually wrong. Converges to only 0. Yeah. Now is it fine?
Yes, sir.
Okay. Yeah, that's good because I also get confused. Okay, now the co-countable topology. Okay, so let X be a set with the co-countable topology. So I will denote it by tau CC. Now, how the convergent sequences in this topology looks like? Then prove that prove that a sequence xn in X is convergent if and only if xn is eventually constant. Okay, so only the eventually constant sequences are convergent in the case of co-countable topology. So let's try to prove this. So one direction is clear. Can you see which direction is easy? No, the backward is clear. So if the sequence is eventually constant, then it has to be convergent. So uh, suppose xn is eventually constant. Now what does it mean? So xn equals to some x for all n bigger equals to n naught. Because after certain stage, all the members are same. That is the meaning of eventually constant. Right? So how to prove that this sequence is convergent? So we'll claim that it converges at x. So take arbitrary open set. G belongs to tau such that x belongs to G. So then clearly xn belongs to G for all n bigger equals to n naught, because xn is x itself. So xn converges to x. So this side is very easy. Now let's try to prove the converse. Now let xn is convergent, and suppose xn converges to x. And what we want to prove is xn is eventually constant. Okay, so now how to prove this one, that xn is eventually constant? So what we have to prove? We have to show that there exists some n naught belongs to n such that xn is equals to x for all n bigger equals to n naught. If we can prove this, then we are done. So how we will prove this? So let's take the range set of the sequence xn. The range set of xn. So then this xn is a countable set. This can be finite also, but this is a countable set. So uh, you take the open set G, which is the complement of F, but you take union with X. So this is an open set in the co-countable topology, right? Because its complement is a countable set. and this open set contains x also. So what can you say? So since xn converges to x, so there exists some n naught belongs to n such that xn belongs to g for all n bigger or equals to n naught. But what is g? So this implies xn belongs to g, which is f complement union x for all n bigger or equals to n naught. So from this, can you conclude that xn is eventually constant? So what is f complement union x? What is exactly f? The range set, right? So xn belongs to the complement of the range set, but it is in x. So what does it mean? So this exactly means xn equals to x for all n bigger equals to n naught. Because this element has to be in this range set, right? But we are not saying, we are excluding that. So it has to be in x. Yes. So xn is eventually constant. Okay, so actually here we are excluding the range set. So only possibility is x. Is it clear? Okay. So there are some more problems in sequences, but let's move now because I think we have enough. We have done enough from sequences. Maybe at least one problem for from countability axioms. Okay, let's do it quickly.
Do you have notes?
Sorry,
Do you have notes on this topic?
not note. These are some problems that I have collected.
If you have more, then can you please share in the so we can check that those problems.
Yeah, okay, I will try to share the notes. But let's focus now because I don't have much time today. Yeah. So let x uh, be an infinite set. Then which of the following are true? Okay, the first option is if every topology on X is second countable, then X is itself a countable set. The second one is if tau is a topology on X such that every subset of X with 2026 elements is open, then X comma tau is first countable. And the third one is okay, similar type of assumption. Maybe I should copy this much. So if tau is a topology on X uh, such that every infinite subset is open, then X comma tau is first countable. Okay, so only three options. So let's try to understand this. So we are starting with an infinite set and we have some statements. We need to check which one is true. So first one is if every topology on X is second countable, then X is itself a countable set. Means whatever topology tau you take on X, your X comma tau is second countable. Then can you say your set is countable?
No, sir.
Why?
Sir, if you take a Euclidean topology on R, then it
No,
is
your X is not an X is just an infinite set. X is not R. And we are saying whatever topology you take on X, X comma tau will become second countable. Then
no,
what
no.
can you say about R? What can you say about the set X?
If every topology on X is second countable.
So second countable means it has a countable basis. Yes, someone commented. Maybe let's check. Yes, exactly. Yeah. So if you take let tau equals to the power set. So this is the discrete topology. Discrete topology on X. Then by the statement X comma tau is second countable. But when a discrete topology is second countable, only if the set is countable. So thus X has to be countable. So we just go to the lectures. It was done there for this when the discrete topology is second countable. Because here all the singleton sets are open sets. So that thing has to be used. So the first option is true. Okay, now let's see the second one. Now, if tau is a topology on X, means we are taking a particular topology such that every subset of X with cardinality 2026 is open. Then this topology X comma tau, then this topology tau is first countable. So we are taking a topology with some particular property. Then we are asking that topology is first countable or not. So what do you think? It is first countable. Yeah, it is first countable, but why cofinite topology you are mentioning? I did not understand. So it is a topology in which every subset with cardinality 2026 is open. That is the property. So why it is first countable?
Sir, is it a topology?
Sorry.
Sir, is it a topology?
No, I am assuming it is a topology, and in this topology, every subset with 2026 element is open. So I am assuming that.
Sir, when you take arbitrary union,
Then
union will not be in the topology. No? Then
no,
how?
these are the not only open sets. There are other open sets, but these are also open sets.
Sir, that every subset of X with okay, sir.
Yeah, so you should understand the statement properly. Okay, that is important. So in this topology, if you take any set with cardinality 2026, that has to be open. There are other open sets also, but those are among the open sets. So it is first countable or not. So to check first countable, what we have to check means what is the definition of first countable? So x comma tau is first countable. So when we say this, if at every element x there exists a countable local base, right? That is the definition. So the thing is both B and C will be true. In the option C, instead of cardinality 2026, we are saying infinite subsets. That is the only difference. And how I will prove this? So for every x belongs to x, so in these situations, what will happen is, in these situations, for every x belongs to x, the singleton set x will be an open set. And so if you take this just singleton set x, this will be your countable local base at x. Okay, so the only thing which I have to show is that this singleton set x is open. So for the option B, can you see why the singleton set x is open?
Yes, sir.
Yes, it is actually very easy. You just have to use the definition of topology.
Takes an intersection of two sets containing 2026 elements and only X
Only
in
common
common.
element is x. And what you have to use is that your set x is infinite. So, okay, so since x is infinite, we can write singleton X is intersection of some A1 and A2, where cardinality of A1 equals to cardinality of A2 is 2026. So this is for the option B. You just try to prove this. This is very easy. And for the option C, what you will do is you can do the similar thing, exactly similar thing where this cardinality is infinite. So maybe I will merge this. Or cardinality of A1 equals to cardinality of A2 is infinite for option C. And intersection of two open set is open, so singleton X will be open. So is it clear? Okay. So maybe let's do one or continuous function. Maybe then I will wind up today. Yeah. Let's do this. Do you have any other doubts so far? Okay, if you have any doubt, just ask, right? Because I can make also some mistakes. So if you ask your doubts, then it will be more clear and it will be helpful for me also. Okay, so check continuity of the following functions. Okay, so the first one is your f is defined from R with the Euclidean topology to R with the cofinite topology, and it is defined as f of x is equals to x minus 1 by 5. And the second one is your f is defined from R2 with the Euclidean topology to R with the Euclidean topology, defined as f of xy equals to just the product. And option C is same topologies, R2 comma tau e to R comma tau e, where f of xy is just x plus y. Okay, so you have to check that these three functions are continuous or not. So let's do this one by one. So we will use the definition for the first one. So what we have to do is we have to check inverse image of open set is open or not. So what do you think for the first one? Okay, so maybe instead of open sets, maybe we can use closed sets. So there is the other characterization of continuous functions, that if f inverse f is closed for every closed set f, then also it is continuous, right? So let's use this one because the cofinite topology is easier to deal with closed sets. So in R tau CF, what are the closed sets? So in R with cofinite topology, the closed sets are
Only
R with
finite.
R and finite sets. Okay, so what is inverse image of R? You can see it will be R itself, because this map will be surjective.
Not an onto.
So this is closed in tau e. And if you take a finite set, let's say x1 up to xn, what will be F inverse F?
Will be a finite set.
Yeah, but we can explicitly describe this set. So this will be 5x1 plus 1, 5x2 plus 1, so on 5xn plus 1. So this is a finite set. And in the Euclidean topology, also the finite sets are closed. And it is closed in tau e. So therefore it has to be continuous. So F is continuous. So the first one is continuous. Now what about the second one? Option B. From R2 to R defined by the product. So here we will use the open set, means the definition, or maybe the characterization by basis. So we know, so what is the well-known basis for the Euclidean topology on R?
Open set. So open intervals.
Yeah, exactly. So where A, B belongs to R with A less than B is a basis for R comma tau E. And we just need to check inverse image of these basis elements are open or not. So now, so what about the inverse image of this? So this is the set of all those elements in R2 such that f of xy belongs to this open interval AB. So all those elements in R2, what is fxy? It is just the product. So A less than xy less than B. So we need to check this set is open or not. Now, can you see why this set will be open, but can you see why it is open? So let's try to see the image. If we draw the image of this set, so it will be like, so here you have xy equals to A, and somewhere at here at you will have xy equals to B, and on other hand also here you have xy equals to A, and here you have xy equals to B, and your set is exactly lies here. So is this a open set? So can you convince pictorially? So is it open set?
Yes, sir. Every point is an interior point.
Yes, exactly. So if you take a point here, can you find an open set? containing this point, but also contained in this region. So you can find a circle which is lies inside this region, right? So every point will be interior point. So just try to convince yourself pictorially. This can be done laboriously also, but I don't want to do that much because it is easy to see if you draw the images. So this set is open in R2 comma tau e. It is easy to see pictorially. Okay, so this will be open. So F is continuous. So option B is also continuous. So what about the third option? Can you do similarly? Okay,
Yes.
in the option C, similarly as in B, what about the inverse image of this interval? This is
It
exactly,
will,
yeah, go ahead.
inverse image will be open, which is continuous.
So it is lies between these straight lines, okay? So if you draw the image, then it will look like here you have x equals to a, and somewhere at here you have x equals to b, and your region is this one. So here also every point is interior point, so this is open set. So F is continuous. Yeah, so all these three functions are continuous. So this will be useful. We'll see later. So this thing is important because we will use this later also. Okay, so any questions so far?
No, sir.
Okay, then maybe let's wind up today, and we will meet in the next week again. Meanwhile, if you have any doubt, you can just post it.
So separable spaces, this is also done, I think, in this week.
Sorry, which one?
Separable, separability, sir.
Separability.
Separability, yes, sir.
Yeah, separability has been done in this week. All the countability axioms has been done. Yes.
Sir, and the third question and what you have written, sir, at last.
In the last question,
Third question last. Third question at the end.
yeah, this one, this solution,
No, sir. The third question itself. At the end, xn converges at the end.
that cofinite topology. Yes, yes.
At the end, sir. You have written one statement xn converges to x not equal to 0.
Yeah, so we want to prove that xn, this sequence converges to only 0. First, we have proved that it is converges to 0. Now we want to show it is not convergent to other points. That thing we have proved here. Yeah, so what is your doubt?
Sir, at the end, what so xn converges to x where x not equal to 0 means it will converge to every point other than 0 if I take
Oh, so,
means.
sorry, this line is not needed. Yeah, you are right.
Yes.
Yeah, so that line is not needed. Maybe I have written that thing earlier. and I forgot to erase. Okay.
Okay, that is the doubt.
Yeah. Okay. Yeah. Any other thing you want to mention?
No, sir. Thank you, sir.
Yeah. Okay. Then let's meet in the next week again.
Okay,
Okay. See you all in the next week.
good. Thank you, sir.
Yeah. Okay.